Okay. Last time I did a general second order ODE where there's characteristic equation, it's quadratic, there's sort of two roots or two eigenvalues, and assumed real and distinct. And then I assigned to you for homework to a complex case. There's one case left where roots are real and the same. That works out a little differently. So okay. So we have y double prime plus p y prime plus qy is 0. Same initial conditions. And as before, rewritten as a first order system. U1, U2 prime is matrix 0, 1, minus Q minus P, U1, U2, where the initial values of U1 and U2 are the same as the original problem, where U1 is Y and U2 is Y prime. So that part's no different. And if I refer to this matrix as A, what we want is e to the AT. Because our solution is going to be e to the AT times the initial values, and then we take a first component of that, and that's our solution, just like I did last time. So what happens when we look at e to the AT? All right. So e to the AT would be equal to x e to the JT x inverse, where A has factorization xj x inverse, and this is a Jordan form. Now, in the case of the eigenvalues of A being distinct, like last time, then Jordan form is just a diagonal matrix, and the columns of X are the two eigenvectors of A. So everything worked out really nicely in this case, in that case. So what happens if the roots are the same? Because so we know what the eigenvectors are from before. So the eigenvalues are lambda 1, lambda 2 that come from the quadratic formula. Okay, so the roots of lambda squared plus p lambda plus q is equal to 0. All right. So then, which happens to be the characteristic polynomial of A. All right. So the other thing I was arrived at last time is the eigenvectors So for each eigenvalue lambda I, an eigenvector is 1 for the first element and lambda I for the second element. Now, if the roots are distinct, then these two eigenvectors are not scalar multiples of each other, therefore they are linearly independent. So you stick them in a matrix capital X, and because they're linearly independent, X has an inverse. So we can go ahead and do this. But if lambda 1 is equal to lambda 2, so in other words, P is equal to, actually, yep, plus or minus 2Q, cause the discriminant to be 0. Then we have a problem that A is not diagonalizable. Okay. Because for diagonalizability, we need a full set of eigenvectors, and we don't have that. Yeah. So a Jordan form, in this case, is not going to be a diagonal matrix anymore. It's going to be a 2x2 Jordan block that has like the eigenvalue done in diagonal and then a 1 in it. So when you can't get a full set of eigenvectors, you still have to complete the whole space. And the way we do that is with generalized eigenvectors. Oh, go ahead. For any questions up to this point, before we actually find generalized eigenvector? Actually, I don't know if you all have dealt with generalized eigenvectors like in a linear algebra class or anything. I don't know if you don't even cover that.
I don't even remember.
Okay.
It was so long ago.
Yeah. Hey, 'cause I don't recall in my first linear algebra class, we learned about eigenvalues and eigenvectors, but never generalized. So you talk about just the diagonalizable case. Okay, so vector x is a generalized eigenvector of A if okay, corresponding to the eigenvalue lambda if we have this situation where if you multiply x by A minus lambda identity, you do not get 0. Because if it were the case, then x would be an ordinary eigenvector. But A minus lambda I to some power p times x is 0.
Okay, just to be very clear, some power p will have nothing to do with our p in the.
Oh, whoops. Yeah,
I just want to make sure. That seems
yeah,
like it would make sense.
Okay, let me just pick a different letter.
Okay.
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 Yeah, so for some power greater than 1, that we do have that. Okay. So, how to find them? Okay. So we let x1 be the regular eigenvector, or n eigenvector. Then you solve systems of equations. A minus lambda identity x2 is equal to x1. A minus lambda identity x3 is equal to x2, and so on, until you're actually not able to get a linearly independent solution anymore. Because what would happen in this case, if you find x2, that would mean that A minus lambda identity squared x2 is 0. The reason why that is, oh, actually, all right. This, well, A minus lambda identity to the first power times x2 is x1. And you still have one of these left over.
Wait.
Okay. We have this.
Mm-hmm.
So one of these lumped in with x2 is x1.
Okay.
So
Yeah. So you're just multiplying. Yeah.
Yeah.
Got it.
Okay. But this is an eigenvector, a regular eigenvector. So that's 0.
Right. Okay.
Yeah.
Okay.
All right. And similar, this would imply that A minus lambda identity cubed times x3 is equal to 0, and so on. Until you're not able to solve for anymore. Now, in our case, we're actually only going to need to do this once, because it's a 2 by 2 matrix. You're trying to fill a 2-dimensional space, because we still want the matrix X from a Jordan form. So one column is the eigenvector.
Mm-hmm.
The other column will be a generalized eigenvector. And now here's where I must confess to my embarrassment / lack of preparation. So I know for that reason that we only need to do this once. There's no point in trying to get an x3. What should happen is that there should be some sort of breakdown if you try to go further. I just don't remember what the breakdown is. So,
It's not going to be like similar, like where if it's a 3 by 3.
well, now if we had a larger space, then yes, you would keep going.
Well, I see what you're saying.
Yeah.
I guess what do you mean the breakdown would be different?
Like for instance, so in this case, since there's only going to be one generalized eigenvector possible, then if I try to solve this system, something should go wrong.
Okay.
I just don't remember what the wrong thing is.
Okay.
But we can find out. So,
Well, maybe.
yeah. So, okay. So, what I'll do is solve for x2. Okay. So in our case, we have A minus lambda identity x2 is equal to x1. So now I have to fill out what that is for our specific case. So we have minus lambda on the diagonal, and then I have a 1 here, and then I have a minus q and minus p times x12, x22 is equal to the eigenvector x1, and we know what that is. That's 1 and like lambda 1. Oh, okay. Actually, I'll just do lambda because we only have one eigenvalue. They're both equal. Okay, so that system has to be solved. Now, the problem is, what complicates matters is this matrix is a singular matrix. But it's still going to be possible to solve the system. Okay, so, but yeah, so this matrix doesn't have an inverse.
Is that what, I have to remember, what is singular, is that what that means?
Yeah, the singular
Okay.
matrix is non-invertible.
Non-invertible, okay,
Yeah. Okay. So, okay, so to go ahead and solve this, I could, let's see, actually, what is the best way to solve this when it's singular? Now, a generalized eigenvector has, well, any multiple of a generalized eigenvector is still a generalized eigenvector, but, so, actually, I think I'll just do this the old-fashioned, the lower level math kind of way. Like, I could do like Gaussian elimination and stuff, but yes, so elimination and substitution.
That's what I was thinking.
Yeah. So we have minus lambda x12 plus x22 is equal to 1. And then I have minus q x12 minus plus p x22 is equal to lambda.
Is that a minus a negative lambda? Or no, wait, it's plus, and that's why.
Yeah.
Right, yeah.
Okay. All right. So as far as eliminating, okay, so x22 is 1 plus lambda x12. So then I can substitute that in here and see what we get. So I have minus q x12 minus lambda plus p 1 plus lambda x12 equal to lambda. This is going to get messy. So, all right, so minus q x12 minus, okay, minus lambda plus p minus lambda squared plus p lambda x12 is equal to lambda. Okay. And
did you just do some factoring in your head of sorts?
Well, I distributed this with this.
Oh, okay. Yeah, sorry, I was going even more stuff, so.
Oh, okay.
I'm trusting you.
Oh, okay. Now, one thing that's going to help us simplify is I can write this as minus x12 times lambda squared plus p lambda plus q is equal to lambda plus p. So what happens here is, yeah, so I moved this to the other side. That's 0. Because lambda is an eigenvalue, it's the root of a characteristic equation. And then what we have is now here I have lambda plus 2p is equal to 0, but the thing is that's also 0. Because when you have a double root from a quadratic formula, it's minus p over 2. Because that's the first part of the quadratic formula, and then you have plus or minus square root of blah, blah, blah. But this is a double root.
Yeah.
So all that square root stuff is 0.
Yeah.
So So in other words,
Which is a vertex too, correct?
well, yeah, it has to do with that.
Okay,
Yeah, vertex of a parabola. Yeah, so the equation is satisfied no matter what I pick.
Okay.
That to be. So in other words, as long as this is satisfied, I have a solution. So I can plug in something for x12, and then I get x22 from that. And it's a generalized, then the system is satisfied because this second equation is a tautology.
Right. So anything works is all solutions to be 0 equals 0.
Yes. So
we're
yes.
still going to just choose one?
Well, yes. So the second equation is satisfied no matter what.
Okay.
The first equation is satisfied as long as this is satisfied.
Okay.
So this is my only constraint. So I can choose x12 arbitrarily,
and
then choose that, and then use this to get x22.
Okay.
So I'll just set x12 to 0.
Okay.
So my solution x2 is equal to, so x12 is 0, and then x22 is 1. So that works as a generalized eigenvector. Now, okay, so any questions about this, including from virtual land?
I don't know if you wrote anything else over there. Okay, so choosing x12 equals 0 yields x22 equals 1.
Yeah. Yep. So that's the solution.
That's it? Okay.
Yeah. Let's see, minus p is equal to okay. What now I'm curious about is, what if I then took this solution and put it on the right side and tried to solve the system again? Because that would be tantamount to solving this.
Right.
To try to get an x3. My hunch is that we get an inconsistent system. That's probably what happens. But I gotta find out. Okay. Okay. Sorry, 1 second. try to solve A minus lambda identity x3 is equal to x2. So now we have same matrix. x31, x32 is equal to 0 and 1. So that would mean that minus lambda x31 plus x32 is 0. So x32 is lambda x31. Oh, that's interesting. You know what? I could stop here. Because suppose I pick x31 equal to 1. x32 is lambda. That's the eigenvector we already have. So whatever solution we could possibly get from this does not add to our basis. Because we're trying to form a basis of eigenvectors and generalized eigenvectors that describes an invariant subspace completely. And there's only point in doing this, continuing this chain, if you will, of building the chain of vectors, as long as you get new linearly independent vectors. Once you can't get any more, then you stop. So in this case, going through this would result in getting a vector we already have. So we stop.
So we choose x31 equal to 1. X32 is lambda.
Yeah, because anytime, because since the eigenvector we already got is 1 lambda, so second component is a first component times lambda. So x3 circles back around to x1. Oh.
Okay.
Caitlin just disappeared. Well, at least we're recording. Okay.
Okay, wait. So x3 is now circling back to x1.
Yeah.
Which means it's not.
There's nothing more to do.
Okay.
Yeah. And we knew already that there'd be nothing more to do because we're.
Right.
Oh, yeah. So. Okay. So now we can do the whole Jordan form thing. Okay, so we have A minus lambda identity x2 is equal to x1. So that's the same as saying AX2 equals x1 plus lambda x2. And we also know that AX1 is equal to just lambda x1 because it's a regular eigenvector. So if we put the two together, describe this in matrix form. So what I'm going to do is A times x1, x2 are linear combinations of x1 and x2. So, all right. So AX1 is just going to be lambda x1, so I put a lambda here. And there's no x2 term here, so I put a 0 here. For the second column, AX2 is equal to x1 by itself, so I put a 1. And then lambda x2, so I put a lambda. And that's the familiar Jordan form, where you have lambdas down a diagonal and the ones above. And so that's actually where that appearance of a Jordan form comes from, because it relates A to its eigenvectors and generalized eigenvectors. So A is equal to xj x inverse, where now we know what all these things are. So x is equal to x1, which is the eigenvector, and then a generalized eigenvector. So it's this lower triangular matrix. And then J is the Jordan form, lambda's down a diagonal, and a 1 above. And this X is easy to invert. First of all, it's lower triangular. So the inverse is lower triangular. So the determinant is 1, so that makes things easier. You swap the diagonal entries, but they're both 1s. And you negate the off-diagonal entries, you get a minus lambda down here. Let's see, how are we doing on time? Oh, I only have a few minutes left. Okay. So now that we have the matrix A factored, you can figure out the exponential. Okay. Using something I worked out a couple classes ago. Okay. Well, first, any questions about this?
I'm good.
Okay. All right, so let's get this exponential and then we'll wrap this up. All right, so e to the at is e to the xj x inverse t, but that's the same as x e to the jt x inverse. So that would be 1 lambda 0 1. Now j is not diagonal, so its exponential takes a little more work, but we'd actually worked it out before. So I'll just repeat that. It's e to the lambda t on the diagonal, and then 0 down here, and then we have t e to the lambda t in the upper right corner.
And that comes back from the block stuff.
Yeah.
Right, okay.
Yeah, we did that before with a 3 by 3 case. And then x inverse. Okay. So now what I want to do is work out the first row of this matrix, because that's all I need for the solution of the original second order ODE. So first row is going to be first row of this. And then times the rest of this. Okay. Now, but when I multiply a matrix by E1 transpose, that's what this is. That's just taking the first row. So now I can take the first row of this. And I factored out e to the lambda t.
Right, yeah.
Because I'm tired of writing it. So now I can just do this matrix vector multiplication, and what I'll get is 1 minus lambda t, and then t. Okay. So then the solution to the original ODE is a y of t, which is E1 transpose e to the AT times the vector of initial values. Okay. But now all of that has been worked out here. So now I just have to multiply that by the vector of initial values. So that would be e to the lambda t, 1 minus lambda t, y naught plus t e to lambda t, z naught. So to verify, what am I doing? Okay, I'm a little past time, sorry, as I get for starting late. If I set t equal to 0 in all of this, lot goes away, and I'm left with y naught. And if I take the derivative, that's going to be a pain because it'll involve the product rule. So I'd have,
That was kind of a funny one too, I think.
all right, okay, so if I take a derivative, so I have lambda e to the lambda t, 1 minus lambda t, y0 plus e to the lambda t minus lambda y0. I said t equal to 0, so that's gone, that's gone, that's gone. And why not? Okay, that cancels out, good. Plus t lambda e to the lambda t z0 plus e to the lambda t z0. And I said t equals 0, and that's gone, and that's gone. And you get z0. Okay, so it's correct. It satisfies the initial conditions. So yeah, this is the solution in the case of a repeated root of the characteristic equation. So whatever initial data you have, you just plug it into that, and that's it. Okay. And then the complex cases homework. So next time, or next thing to get into would be, because my ODE had 0 on the right side. What if we have a function there? What do we do in that case? So, yeah. Whew. All right. Okay. So until next time. Well, I'll see you in 25 minutes.